So what we would like to do today is we would finalize a little bit our discussion of linear parabolic equations, where we have now seen existence, a proof of existence for weak solutions under quite weak assumptions, in particular also for the right-hand side, only requiring that's an of course L2 in time, but only h-1 in space function, allowing for concentrated sources. So, as you know already, one important property of elliptic and parabolic equation is the maximum principle. The maximum principle comes in various versions, very weak formulations up to very strong formulation. The most strong formulation, which holds also true in the parabolic sense, but only for classical solutions, is that if a maximum is attained in the interior, the solution is necessarily constant up to this point, so to speak, in the parabolic cylinder up to this time level. And then that would be the strong maximum principle. Then there are weaker forms only saying the maximum is attained at the boundary, and as a consequence there are comparison principles which then ensure uniqueness. And a most weak formulation, which also holds true for this general solutions which we have, is the following. So we are looking at a solution in the most weak sense, so L2 in time, H1 in space, should be a solution of, let's say, our standard equation, but that is not so important. So this minus Laplace of u can also substitute it by a general elliptic operator. The only thing one has to take care of is the zero order term which appears in it. So there the corresponding signs have to hold. But for example, first order terms, convective terms, there's no restriction whatsoever. But we formulate it here in this form. First of all, for the homogeneous case, I will say something for the inhomogeneous case in a second. And okay, then we have initial data, and we have boundary data, which are here supposed to be Dirichlet boundary data. A bit strange, okay. Delta omega t. Okay, so the assumptions, the regularity assumptions are supposed to be, okay, u0 being an L2 function. This was the most general situation which we had. The g is supposed to be an L2 function. So the g to be understood as the prolongation, as a necessarily existing prolongation of the boundary data, because the g has to be a trace in space. So in the prolongation it should be an h1 function. That's the one thing. And we have seen what we further at least need to do the way we did the proof, namely, so to speak, subtracting the g from the problem. We also need something on the time derivative of the g. So we need something on h1 in time. But here we only need very weak things, namely to be a dual element and being in h-1 of omega. So that's the standard assumption. And this very weak formulation of the maximum principle is the following. If there is a bound for the initial data, Of course, that means it's actually an L infinity. Does not mean it's an L infinity function because it's only a one-sided statement here, but it goes in the direction. The same thing for the Dirichlet data. So we then the consequence is that the whole solution U is also less or equal to this constant on Qt. So that would be a result which follows from all the other versions of the maximum principle I have stated. So in this sense, it's a very weak formulation, but it already requires weak assumptions. So what kind of... so first of all, the same thing, of course, could be also stated as a minimum principle, because then we just look at minus u. This is possible because we have here a homogeneous equation. If we would have an inhomogeneous equation, the question is how, in which way the sign of the right-hand side and the sign of the source comes in. And the proof, basically the proof, is just comes by, at least formally, the proof is very simple. To make it rigorous is not that simple. The formal proof is we just test with a specific function, namely with a test function u minus m plus. What we would like to see is that u is less or equal to m. That is, we would like to see that the plus part of this function is 0. We'd like to prove that this phi is 0. That is, to show is phi is equal to 0. And if we do, the question now is a little bit how to do derivatives with this, how to compute derivatives of this function here. Because as you will imagine, there is, so to speak, the set u equals to m. And at the set u equals to m, typically this function will be continuous but not differentiable. So we can only deal with weak derivatives, and we have to know how to compute the weak derivatives of this function. And how to compute the weak derivatives, this is that there is something which is called Stampacchia's lemma. With 2c, Stampacchia's lemma, that tells us that if we would like, and that is for the gradient of phi, we can compute as we would like to expect. So what we would like to expect in the set where u is strictly bigger than m, of course the gradient should be the gradient of u. And in the set where the u is less than m, then we have a 0. Then of course the gradient should be 0. The only question is what happens in at the set u equals to m. But you might remember this consideration in conjunction with conformal finite elements. What is a conformal finite element? There we require that the ansatz functions, which are locally composed of, say, polynomials, are patched together continuously. And we need this because that is the characterization that a function which is patched together by, let's say, polynomials or other smooth functions, but is not differentiable at the interface where they come together, that this function nevertheless has a weak derivative, which is just defined as the weak derivative in the corresponding subsets. And if those derivatives at the subsets are L2 functions, or we get an L2 derivative, we get an H1 function, we stay within the ansatz space. And that is very similar here. We don't have polynomials, but it's in the same direction. So The statement is that this intermediate set u equals to m does not make any harm. So what comes out here is really the gradient in the one set and the 0 in the other set. And this we can write in this way, where psi is the characteristic function. So 1 or 0 correspondingly the characteristic function of this set u bigger than m. So for smooth functions, it's all quite clear, and Stampacchia's lemma says that this also holds true in this setting of H1 functions where we are here. So, but now having this test function here in the time-dependent situation, in the weak formulation, what we would like to do is to have a time derivative, not an x derivative, not a gradient. So what we do is, what we conjecture, so to speak, is, and that's the formal part of the proof, that for the time derivative, the situation is the same. And if this is the case, then we plug this in, this test function, and then we can then we get actually our result, namely we plug it in. So we have here the test function, time derivative of u. So that's not yet okay, plus gradient u, gradient v, gradient phi, so that would be the weak formulation. And this we can write now as, so this part we can write now as, because we can always, the difference between the derivatives, so we have, what this says, it's either phi and u have the same derivative, or it's 0 and the whole thing is 0 and does not contribute. So we can write this now as substitute this by phi, and then write this as a derivative, as a time derivative of 1/2 phi squared. And here, by this one, we just get the same situation, so we get gradient of u squared. A gradient of phi squared we would like to have. Whether we write it in u or in phi, that's, as this formula says, is no difference. Okay, and that's basically is it, because that means if we differentiate, what can we do? We can integrate this out. If the test function is such that it vanishes at the capital T, only the point at 0 remains. At 0 we have then minus 1/2. And what was the phi? That was the u minus m plus at the u0, sorry, the u0 minus m plus, we had a t equal to 0 in L2 squared. And here we have this term. Okay. Okay, so what does that mean? This term here is 0 by assumption. And now the question is, where have we used the other boundary, the sign condition on the boundary? This we have used in the partial, in this identity setting here, because that means that the phi is 0 at the u equals to m at this interface. Okay, what does that mean? This part here is non-negative, and that means phi is equal to 0. This this part is less or equal to 0. The gradient vanishes at the boundary. At the boundary, phi is equal to 0. This comes from this g less or equal to m assumption, and then we have it. So that was formal because we all have had this conjecture. Rigorously, we do, and I do not do this in detail, rigorously we do it time discrete. That is, we show it, we look again at our implicit Euler method, do the thing for the implicit Euler method. There we don't have a time derivative, so this question does not come up if we do this testing with a u minus m plus at the corresponding time level. So we get this result at each time level, and then we have to see that our convergence is good enough to get this result through to the limit. Okay, so what would be the situation if there would be a right-hand side G? We see that we then need a sign condition that this term gets a right sign. So if the G is less or equal to 0, the same thing holds true in the same manner. But that means if we now want to have a minimum principle, the sign condition reverses. So there one has to be a little bit careful. Okay, that was one remark, and the other remark refers to how can I glue together solutions of parabolic equation. Quite often, if one wants to show, so as we have this time interval, and we have to distinguish two sorts of existence results. What we have seen up till now was a global in time existence result. We have given a time interval with no restriction of its length, and we have shown there is existence of a solution. That does not mean that the solution does not depend on the length of the time interval. So often the weak estimates we get out is that the solution might exponentially increase in the length of the time interval, something like that. That is not excluded. So it's not said that the solution is globally bounded or something like that on whole R plus. But global existence in the first glance means there is a solution on any time interval, irrespective of the length we would like to have. The weaker statement is local in time solution. I would claim that for nearly every problem, time-dependent problem, local in time solution can be proved. That's a little bit courageous now, but I think I cannot, at the moment, I cannot imagine any problem where this does not hold true. Of course, it's a very big problem whether this is then a global in time solution. And if one goes then to the Navier-Stokes equation, one could even earn money with this question. For the Navier-Stokes equation, it's clear that there is a small time interval where a classical solution exists. This time interval depends on the size of the data, but it's not clear whether there's a global in time solution. And it might well be that these things also fall apart whether one looks at classical solutions or at weak solutions. So how can we prove global in time solutions if the situation is not as easy as we have it here? So typically what will happen is that one first gets a certain time interval. And then the question is this time interval, is this the end of the story, so to speak, because then the solution develops a singularity or whatsoever? Or is this a time interval which has a maybe very, very small, but length with a, so to speak, uniform lower bound in terms of the data? So can we take this time interval and glue it together? Can we go with the solution to a certain time level, then having the same situation as before, start again there, going the next step again, and so on. It's like time stepping in the discretization method. And to make this possible, that is put together in the next proposition. Maybe I call it gluing together of solutions. So what do we have? We have time points t1, t0, t1, t2. And we have right-hand sides and further assumptions that are good for the full interval, so for the interval t0, t2. So here h minus 1 of omega. And do we have... No, we don't need this. And then we start up with a solution, then U1 is supposed to be a solution in the first interval from t0 to t1. So this is an L2 t0 t1 h1 of omega function. So we don't have to look at the boundary conditions here. This argument is good irrespective whether we have here Neumann or Dirichlet or whatever kind of boundary conditions. This is supposed to be a solution, corresponding weak solution of the heat equation. Let's say in this first interval. And let's say U2. That starts at T1, goes to T2, same thing, is also a solution of, again, the heat equation now in the next interval from T1 to T2. So now these things have to come together. So that means in the trace sense, U1 at T1 should be the same as U2 at T1. So that would be the case if we say the second is a new problem and we start, let's say, to make it easier, we have assumptions, we use the continuous representative. We use that the solution, as we have seen, is continuous in time with values in L2. Then it's easier. We have not to talk about traces. Then we just start with the last time level of the old solution, get the new solution. And let's say obvious, but nevertheless assertion which has to be proved is then. If we glue the solutions together, that is, we have U1 here and we have U2 here. Doesn't matter where we put the T1 to which interval is a solution on the full interval. So what we have to do is, okay, it's quite simple, and maybe I skip the details. That is a solution. There's again as a formal part of the proof, namely to check that this composite thing is a solution. That we get immediately by the weak formulation. because the trace terms which we get putting the time derivative to the test function, the trace terms just cancel each other. That is this condition here. That's very, very similar to the Stampacchia thing and the conformal finite element thing. What we have to know is that if we glue these two functions together, and that is then again also in this framework, if we glue these functions together and we have h1 functions, that is, so if we now want to go higher so next step would be to go higher, really to see that there is a time derivative as a function if the same thing holds true for the subintervals. That means the following: if we glue together two h1 functions in time, under these conditions, this should again be an h1 function. And very similar to the other statements I just mentioned. And that is true, and the derivative is just the derivative of the u1 at the first interval and times the characteristic function plus the u2 at the second interval times the characteristic functions of the second interval. So in this sense, we not only get then, maybe I don't write this down, in this sense we not only get solutions which time derivatives in h minus 1, but we can also glue together corresponding solutions of higher regularity and get it together. And that is then the background, as I have explained, to glue together solutions which are achieved on bounded intervals to come to, finally, if possible, to a global existence result. So, what we have seen already in the looking at the solution representation, for example, with the fundamental solution and things like that, that actually, if the data are what we would like to expect is that the solution, even for not so smooth data, actually of a parabolic equation is very, very smooth, the C infinity in the end. And the only thing which can prevent it from being C infinity is maybe something in the coefficients, that they are not smooth enough, or something in the domain, if there are strange boundaries in the domain. But if we stay away from the domain, if we stay away from t equal to 0, there should be strong regularity. So the way to conclude this here on the level of weak solutions would be to go on, so to speak, in the way we have dealt here. So what was the basic thing what we've done up to now? We tested with the solution. That was, in principle, that was the only thing what we have done. Then if we would have a time derivative as a function, of course we can also test with a time derivative. And in this way conclude something about the time derivative. Of course, up to this level, this is only formal, because if we don't know that this time derivative is a function, so again, one can make this rigorous going through the time discrete approximation. So what we can do is we can let me write it down. There is only one possible version. There are a lot of further ones. Of course, we have to so again we look at, we have a solution U from, so standard regularity first. Let's say Dirichlet, homogeneous Dirichlet data, because now the boundary data play a role of heat equation initial data. And do we have, I think we have homogeneous Dirichlet data. I write it again. Okay, so if now the right-hand side is a smoother, or let me rephrase it. What can prevent regularity are, as I said, three things. Bad coefficients, okay, this we don't have here. A bad domain, we haven't said anything about the domain, so we will not now come up to C infinity in one step. And a bad right-hand side. So now we look at the improvement which comes from a better right-hand side. How far do we get if we improve on the right-hand side without doing anything on the domain? Okay, so what we now assume is that this is just an L2 function. So no function, no distributed sources anymore, just a smeared L2 function. And if this is so, and also the initial data should be from H1 0 omega, so smooth in this sense, smooth initial data compatible with the boundary conditions, and it's claimed that this is not necessary. I'm not so 100% sure, but if he says so, okay. Okay, might be. So, and then, and I only state this, and I have said already as how the proof works. Then we know that the time derivative of u, which up to now was only an L2 function, which elements in the h minus 1, is now really an L2 function. So in this sense, we now have a strong solution, what's also called a strong solution. So in this hierarchy of notions, we have classical solution, everything exists pointwise, is continuous, and so on and so on. We have the weak solutions, the derivatives possibly do not exist, they only exist as functionals. And the strong solutions, the derivatives all exist as weak derivatives and are functions. So in this sense, then we can just write down the equations without dealing any weak formulation, because everything then has a sense. At least the time derivative makes sense. And then we have to see also something about so we are not yet at the strong solution, because what we have here now is that the time derivative makes sense as a function, but we have not yet seen that the Laplacian of u makes sense as a function. So we have not yet seen that u is in H2, not only in H1, but in H2. But this will come in a second. So first of all, we have a little bit more for the u in the sense that it's bounded in time with values in H1, not only L2. And now this other ingredients comes in, namely the smoothness of the boundary. And this is quite a strong assumption which can be weakened. If omega is of class C2, what does that mean? That means we can parameterize the boundary of the domain such that the describing function is always so we have an atlas of mappings and so on, and the function is always a C2 function. That means what of course is excluded is a rectangle, or even something smoother than the rectangle, which is not very convenient here. It's really quite, basically we are down to something like circles or other potato-shaped domains. So if this is the case, then also the second derivatives exist as a function. That is, u is then an L2 function, 0t, and here h2 in omega. So we have second derivatives, Laplacian. So then we have a strong solution. So we have, if we look here, so this is then an L2 function, this is an L2 function, and this f, therefore we need it, this is also an L2 function. This is just an identity, the heat equation is just an identity between L2 functions. Okay, so I just mentioned this by passing. This is a very strong assumption here, and this can be relaxed, and we can come to basically the same result. If we go down here, I would say we can go down to Lipschitz domain, but the domain has to be convex. So the thing which destroys regularity in elliptic problems in terms of the domain are re-entrant corners. And maybe you have seen these examples with re-entrant corners, that if the more re-entrant the corner becomes, so depending from which side you see, the larger the angle gets, the more the regularity goes down. And the extreme case would, of course, be, so what could you have? You could look at something like that. You could look at something like that, and it's getting worse and worse, and in the end, it would be something like that, a domain with a slit. It's a sort of a crack model or whatsoever, and then everything is gone. Then we not even, in this situation, we not even have the absolutely basic assumption that the domain is at one side of the boundary. So all these things can handle, this can is basically, in this type of theory, it's impossible to handle that. And what we see here, that the larger this angle gets here, the more the regularity is decreased of the solution. And this is a little bit reflected here on a general level, saying if this is not the case, if we have convex domains, then we can preserve this H2. Okay. Up to now we have only dealt with equations. Up to now we had a scalar equation. And now the question is how to go to systems. And there is an easy answer, which is not 100%. So what would that mean? That would mean we have here a function u, which is from omega t to some Rm. So we are dealing with vectorial quantities. Let's say we have the transport of reacting species, and we have m species which are reacting with each other. And the question is, of course, then nonlinearities come in. This is another story to deal with nonlinear problems, but with respect of the parabolic operator, what can we handle? And the parabolic operator would be something like that: time derivative of u. This is now to be understood vectorial. Minus, do we write it minus or plus? Not 100% sure. Was it minus L of u or plus L of u? I think it's plus L of u. Plus L of u. And L of u is now also a vectorial second order operator giving back a vector. And the right-hand side, f is also a vector, of course. F is now also, of course, from omega t to Rm. And then plus boundary conditions and so on. The question is, what kind of L does make sense? If we say we would stick in this framework of, say, diffusion, Fourier's law, or Fick's law then for species transport, we would like to, then the most simple situation would be, of course, if the L would be a diagonal operator. Then that at the discrete, that is only the second, in the ith component, only derivatives of the ith component here appear. Then, at least at this linear level, this is no new problem. These are M independent problems then. M-independent scalar problems. The dependency of these problems would then come in this example of reactive transport, that now the F would be supposed to describe the kinetics of the reactions, and there then the interactions of the species would come in. But one can also have the situation that there's something what is called cross diffusion. That is, the gradient of the species I influences the transport of the species K. And if we would allow for that, then the L of U can have the following general linear form as a second order self-adjoint operator. And then we can also add first order terms and so on. So what do we have? Maybe I first write it down. So the n is the dimension. Omega is a subset of Rn. N is the spatial dimension. M is the amount of species, let's say. So we go here over all spatial variables. We go here over all species variables. And then we have, and that is something which should be a little bit familiar to you, and I write it in this notion of a fourth order tensor with two, do you like this notion of tensors? A fourth order tensor with two covariant and two contravariant components, therefore two up, two down. If you're used to it, it makes sense. But if you're not used to it, it's strange. Okay. But it reminds you hopefully something, namely the corresponding thing in Hooke's law. And it's very similar to that. And what do we have here? We have here the J's derivative of the ith component. And here, to make it, here we have the ith derivative of the whole thing. Let's see, is this all okay? You see, we always have, that's nonsense, it must be L. And you see, you can also check in this tensor formulation, you can always check whether things are correct. And then, of course, also forget about the summation sign, that there's always summation over indices. Where's my K? There's always, and then my K is here. That's a. Okay, we see. It's good to speak about it because then it. So the K is a free parameter, and all the other parameters are bounded. So there'll be sum over these parameters. And in this tensor notion, you always sum about parameters which appear in this up and down form situation here. So that's always a good check whether this makes sense or not, what you have written down. Anyway, so what do we have here? So we have, so to speak, for each component, we have a diffusive part of all possible components, which we just add. So we have cross diffusion of all other possible species. And the only question is, or the question in terms of the existence proof is, can we handle that in the sense, do we have a coercive operator? If we now look at the basic space is now the H1 or H10, depending on the boundary condition, component-wise. So in brackets M, each component in H1 or H10, is this then a coercive operator? And the assumption is, as we have seen already, the assumption is that what we have to have, and that is quite restrictive. So if this holds true, what I now write down, then we can basically repeat the whole theory. So we take here this tensor, we multiply, so to speak, not with vectors as we would to do it if we would have a matrix here. if we would have a tensor of second, whatever this is in English, Stufe, level, second order, and now we have fourth order, and now we don't multiply here with vectors, we multiply with matrices, xi and xi, and again, oops, there we see already something is wrong with my indices. This is supposed to be in L, and this is supposed to be in I, so this, and this, so seems to be okay formally. This should be strictly positive, or equivalently should be bounded from below by some positive constant gamma times some norm of the matrix. Here we can take whatever we want, as we know, and this has to hold for all matrices for all xi from R and M. And if we again remember the situation in materials, we know that this does not hold true. It only holds true for the symmetric matrices, and we have to what comes up there, and then we need further assumptions and so on, and have to deal with Korn's inequality. So this is a very strong assumption which goes in here. If we would have this, everything is fine with systems, but it does not mean that we do cover very many systems with that. Okay, maybe we leave this as it is. As a final remark, the other things maybe we can skip. And now come to the wave equation. Okay. So we have seen the wave equation appearing already in several places. I will only briefly remind them. So what is the wave equation? It looks at first glance very similar to the heat equation, but it's actually totally different. It's, let's keep here a constant, c square, because then this is the wave speed, which we cannot scale away. Because what we would like to do is we would in particular look at this equation in particular for omega equals the whole Rn. So in the first class we would look for solutions of this equation on the full spatial domain. So we've seen already that this appears in elastic media. If this is, so to speak, the most simple situation of Hooke's law, which comes in here, and then we get this form here. So we get this in elastic media. We get it in pressure waves in gases. We have also seen that we can get it in electromagnetic waves. So if we have the Maxwell equation, then if we put the rotation operator on the Maxwell equation, then for the electrical field, again, a wave equation comes out. The funny thing is that water waves, where one would expect, of course, that's the most prominent examples for the wave equation, does not fulfill the wave equation. So if I would like to describe water waves, in the most precise situation, we should do this with the Navier-Stokes equation, which what is called a free surface. And then there are various approximations to the Navier-Stokes equations, which come by averaging over the height, or maybe also other types of averaging, which are then called the shallow water equations. So these are also equations of hyperbolic type, whatever this means. So this we have to find out, in which sense these equations are now different than the parabolic equations, but they are not the wave equation. So let's keep it at this level first. And so then we need initial data. And as initial data here, as we have two time derivatives here, let's think of a time discretized version. Then this would be a system of linear ODEs then. And then you know that to make a system of an equation or a system of ODEs with a second order derivative well posed, you need two initial data, the value and the derivative, and correspondingly for higher order in time. So we need not only the u, we also need the time derivative of u. Okay, so maybe we will not really come up to the existence proof right now, but what this last 20 minutes or so, yeah? No, we have more. We started at half. Okay, we have more. So first of all, we would like to discuss a little bit of explicit solution formulas, which show the different behavior of this type of equations compared to the heat equation. Remember the situation with the heat equation. In a similar situation here, what do we have? So we have then a representation of the solution which comes from a convolution of the fundamental solution with the initial data. So that means every instant in time and every point in space is influenced by every initial data. Of course, extremely little, because there's enormous decay in the fundamental solution, but the fundamental solution is strictly positive everywhere. So it really brings in an influence of every data. Now let's have a look what the solutions look like here. Explicit solution formulas. Okay, and this is very much depending on dimension. Of course, we are interested in n equals 1, 2, 3. N equals 1 is the most simple, as to be expected. Then the next most simple is n equals 3, and from n equals 3 we can conclude n equals 2. So I just write it down, the solution, and we don't prove that. We just there's somewhere something missing. Oh, is there something missing? There's a C missing, and there's a little bit. Okay, this is the formula for C equal to 1. I keep it as it is here. It's not very well done here, actually, from the book. Of course, what we can do is we can do a scaling here in space or in time and get the C equal to 1. But then we have to be aware of this scaling. And as we will see, the C plays the role of a wave speed. And what this means, a wave, we have seen this already a little bit with the notion of traveling wave, even appearing also in nonlinear parabolic equations, but here it will really come up. So let me just write down the solution. The solution is the following. So the first part, which is comes from the initial data, is this one. from the u0, from the displacement, if you want, is this one. And if we would have a c, it would appear here. That, yeah, of course, you do a scaling of the time and so on. So let's first look at this part. So first of all, the solution does not depend on the full initial data, but only at 2 points, which vary with time. So what we have is a sort of a triangle in 1t, or a cone in multi-t, starting at xt. Then we go back along the characteristics, which are here the lines x equals t or x equals ct. And then where we hit the time the t equal to 0, these values define the solution, but not more. And we go back, so we have 2 waves here, the one wave going with the speed c, and the other wave going with the speed minus c. So what we do here is we take the initial data, let it shift with a constant speed c in one direction, say to the right, and with a speed minus c to the left. And this average value here is the solution. That is the claim. So there's only this interval x minus t, x plus t of initial data which influences the solution at that point. What would happen outside does not play any role for the solution at this instance of time. This is what is called the domain of dependency. So in hyperbolic equations we have a bounded domain of dependency. And that is, of course, then also of importance for numerical methods, that numerical methods have to have the same domain of dependency, that they should not allowed to take values outside. And this then again gives a space-time restriction, which is then called the CFL condition, the Courant-Friedrichs-Levy condition, or the condition of the Courant number you might have possibly seen already. Okay, so this is up to that point, and then we still need the influence of the second boundary condition, and that's the same thing. And the interpretation is the same. Here it's the full interval which influences, but it's only this interval. So if we draw a picture in x and t, the situation is like that. We have this point, we go back here, x minus ct, we go back here, x plus ct, and it's only what happens here which influences the solution. Okay, there's not so much more to say. Of course, now we can plug in this, and of course, that to have a classical solution, we need corresponding smooth u0. So u0 has to be twice differentiable to plug it in, and u1 has to be has to have one continuous derivative to have classical solutions. This does not say that these formulas do not hold true if the u0 and the u1 do not fulfill this regularity requirement. Of course, what we would also like, for example, have something like a u0 with a jump. But then we have to work with weak solutions. Okay, so in the following, we only look first at the situation where the u1 is 0. And apparently what plays an important role is this averaging operator. So we give this a notion. So we call mu0 for some function u0, which here was the initial data, is this averaging operator, meaning we take the function, go plus t, minus t, and take the average of these two values. Okay. The question is this also a solution of the of the wave equation in higher dimension, this average. So we just plug in this average into the wave. We just see what kind of equation is fulfilled from this average. And unfortunately, it's not the wave equation in higher dimension, because what comes out is the following. First of all, we have to do it now in higher dimensions. Of course, then we would like to have n equals to 2 and to 3 only. So what do we need here for the construction? We have here the sphere of the ball with the radius 1. That is what this notion is supposed to indicate. And of course, the dimension of the sphere is now n minus 1. And we have here the corresponding surface measure, which is denoted by omega n. So this would be, something like a Hausdorff measure. I'm not sure whether we really need this notation. So it's the n minus 1 dimensional Hausdorff measure of the S. But okay, it's just a sphere. We know what the measure of the sphere is. So what is now the definition in general dimensions? The definition is, what do? We go over all the spheres with radius t, ts. Now I have here two variables, x and t. So what is this supposed to be? I go over the sphere with radius t. That is what I did here also in one dimension. The sphere in one dimension, of course, consists of the points, of 2 points. And I average, this is now the integral, this was just this 1/2 and so on. There, I average over the values x plus xi. So in one dimension, this was the plus t and the minus t, and the average over that. In the corresponding, not so sure whether we need this notation, but okay, anyway. So that's the definition. And now, of course, we can transform the whole thing to a fixed domain. And we have the average here. That is, we subdivide by this measure here. So write it explicitly. We have 1 over omega n. And now this ts we can transform to the integral over s. And then we get here in the function u0, we get the t in here. So that's just a simple variable transformation. We go from the variable xi to the variable t times xi for a fixed factor t. This also has no contribution furthermore, so that's just it. Okay, so that is what is called the spherical mean. So now let's have a look what kind of equation the spherical mean fulfills. And I'm not going to work it out. So what we just do is we compute the Laplacian of this. So we define a function omega, w, as this spherical mean of some function v. And the v is not specified up to the fact that we need some differentiation properties to do the differentiation. So And now the equation which this function fulfills, that is the claim, is what we would like to have is we would like to look at two time derivatives, and then the Laplacian. But that's not all. We get an additional term, that what comes out, and the additional term is n minus 1 over t times the first time derivative of w. And you see for n equals to 1, that's all okay, but for the other n's, it's not okay. Okay. So the Ansatz now for n equals 3, because of this, the Ansatz for what we are taking is that we look at the function. Need another letter. What kind of letters? Let's call it u now. And we multiply this w, the spherical mean, which we have defined, by t. Now we do the same thing. This n minus 1 is now 2 here. And if we now, this is just elementary computation of derivatives. If we now plug this in, we get out that the second time derivative of u minus Laplacian of u is equal to 0. So this additional term gets cancelled by the additional terms we produce by the factor t here. So now we have a solution of the wave equation. The question is for which initial conditions. Okay. So let's look at this function here. And let's assume that the w is bounded. That means the uxt goes to 0 for t to 0. That this is, so to speak, a solution for u0 equal to 0. Hopefully not for u1 also equal to 0. Now we have to compute the u1. And let's compute the u1. So let's look what the time derivative of u is doing. The time derivative of u, we can just compute this. This is the w plus t times the time derivative of w. So if this is also bounded here, this term goes to 0. And this term, what does the w do for t going to 0? Maybe we see this directly from the definition. Here in the definition, we, so to speak, shrink to the one point x. And don't worry about regularity of the function. At the moment, we assume that all kinds of regularity what we need for the functions to do the computations, to get the formulas. So if we let the t go to 0, the w shrinks to, shrinks to 1 point, namely the point x. And as long as the integrand is continuous, then this mean just converges to u0 of x. So what we know is, let's note this somewhere. If the u0 is continuous, then of course the w, the m of u0 xt converges for t to 0 to the u0. So here we get the u0 out. So we are now half done. We have here a linear problem. That is, we have the principle of superposition. We can add solutions, and the sum of solutions is again a solution of the, say, PDE, and the data, if the data operators are also linear, add correspondingly. So we can set up this equation from this solution from a solution from U0 equal to U0 general, U1 equal to 0, plus another solution U0 equal to 0, U1 general. And if we wanted to have also then a right-hand side in addition, we could look for the right-hand side with both initial data equal to 0. So what we now still need is a solution. We have a solution now for U0 and U1 equal to 0, and we still need a solution for U0 equal 0 and U1 general. And this we do in the following way. Let's also call it U, and to the following ansatz. We again take this T times Habe ich jetzt was falsch gemacht? Sorry. This is the other way around. So what do we have? We have here now U0 equals to 1 and U1 general. The U1 here at the moment is still called U0. So we have to take the U1 function in the spherical average here and then multiply with the T. What we now still need is we need a general U0 and U1 equals to 0. And the ansatz which we try to do is the following. We take again the average, the spherical average times T. But now from this we also take the time derivative. And then now I skip first of all, we have a linear problem. If we take any derivative, we have no right-hand side. If we take any derivative that's of a solution, that's also a solution. Let's say, as I said, no worries about regularity. The only thing is what we have to check here is what about now the data, and this now fulfills the data requirements what we would like to have. So if we look at this, what is this? We differentiate this out. We get the mu0. We get the t times time derivative of it. So this goes to u0, and this goes to 0, assuming that this thing here is bounded. So that's the one requirement. And the other requirement, we have to look at the time derivative. So here we get now a second time derivative of the t mu0. So this is what we have here is a solution of the wave equation. So we have here the Laplacian of this thing. And because of the t, again, assuming that the Laplacian of this average is bounded, goes to 0. So we also have this, we have now these other versions. So what we have to do is I don't write it now explicitly, what we have to do is we take this average for the u0, multiply it with t, we take this average for the u1, multiply it with t, and take the time derivative and sum up these two functions. That is the representative That's the solution. And now, how to deal now with 2 dimensions? Maybe I only say it in words. We can deal with 2 dimensions if we just say, okay, this 2-dimensional problem is actually a 3-dimensional problem, but it's independent of the 3rd dimension. So we now have to apply this formula, which we now worked out in the specific situations, and some integral computations come up, and then we get a corresponding formula for the 2-dimensional case. Okay. What is now still missing is the right-hand side. Here we can refer to the situation as we know it from ordinary differential equations. In ordinary differential equations, if we can solve a homogeneous equation, we can also solve the inhomogeneous equation. That is what is then called the variation of constant formulas, or Duhamel's principle. So what one then has? One has a sort of a solution operator which maps the initial data to the solution at a certain instant of time t. Of course, we need unique solutions for that. And the Duhamel principle, the variation of constant formula, just says take this solution operator, so to speak, to the convolution between this solution operator and the right-hand side. Look at the integral from 0 to t of s t minus tau g tau. This is for first-order problems. Now we have here a second-order problem. But we can rewrite a second-order problem as a system as a first-order problem. So the procedure would be we write this as a system of first-order problems by introducing the first time derivative as a second variable. Then we have the second equation, time derivative of u is the new variable, and this is the first time derivative of the new variable. So we have a system. And for the system operator, one has to apply this variations of constant formula. Okay, so next time the question is what to do in general. So this were now basically all for the full domain, so no boundary conditions. And next time we will give an existence proof for the general situation, again by discretization, but not by discretization in time, but by discretization in space, and reducing then to auxiliary to systems of ordinary differential equations. Okay, let's stop here.